Okay, here's solutions for free response number 1. This is good old practice problem here. So we've got summary statistics for data related to latitude and January low temperature. So we've got the latitude in January low temperature. So let's see, degrees Fahrenheit, degrees north. Okay. A view for 55 large U.S. cities. The scatter plot suggests a linear model, so we're going to say, I'm just going to go like this, say it's something sort of like that, because the lower the latitude, degrees north, the closer you are to the equator, the higher your low temperatures are going to be. Okay, write the equation of the least squares regression line that predicts the U.S. city's average January low temperature based on its latitude. So we're going to have January low equals something times the degrees latitude plus a constant, right? So this, of course, here is my slope, and this is the y-intercept. Now, if we're given the data, individual pieces of data, I could put it on my calculator and do linreg, and that'll give me the equation of the regression line that goes through the middle there. But we don't have that. We've got summary statistics. Now, on your formula sheet, you're given this information, B0 plus B1x, I believe is what they use on the front sheet, and then it tells you B1 is R times Sy over Sx, and B0 is Y bar minus B1x bar. Okay, so these are formulas knowing the summary statistic, which is this here. I can just plug them into these two equations and figure out what B1 and B0 are, and B1 is the slope and B0 is always going to be the y-intercept. Okay, so if we do that real quick, B1 is R negative 0.848 times Sy. Remember, these are my y's and these are my x's over here. So 13.49 over 5.42. And then B0 is the y average, 26.44 minus B1, whatever that number is, times x bar, 39.02. I'm going to go ahead and do these on my calculator here. Okay, so after I do those calculations, I've got these values right here. So my January low is going to be B1 negative 2.11 degrees north latitude plus 108.80. Okay, so there's my equation. B, interpret the slope. Remember, the slope is this guy right here, negative 2.11 degrees Fahrenheit. I can always write that as a fraction over 1 degree north latitude. So what does that tell me? That says, on average, an increase of 1 degree north decreases the January low temperature by 2.11 degrees Fahrenheit. I don't need to replace the negative because I said decrease. I don't want to say decrease by negative 2.11, right? It just goes down. For every degree I go up north latitude, the low temperature goes down 2.11 degrees Fahrenheit, right? Okay, so for every degree I go up, I'm on average going down 0.2 degrees. Okay, let's see. Do I think the y-intercept is meaningful? Well, that means at 0 degree north latitude, which is the equator, right? That tells me that the January low is equal to 108.8, right, the predicted. Okay, low temperature of 108.8 does not make sense. Why does that not make sense? Because my data is here. If I were to keep on extending it, this line, I mean, at some point here it's going to curve off, right? But for the data I have with my 55 cities, that's all this data down here, okay? So that doesn't make a whole lot of sense. In D, for a certain city, the residual is negative 4.2. Remember, the residual is y observed minus y predicted. And it tells me that the residual is negative 4.2 degrees. So what does that mean? That means that for that city, that means the predicted value must be greater than the observed value for it to be a negative number, right? So it means this model for this city predicts 4.2 degree low temp. What do we say it was? This is bigger than the observed value. The model for this city, let me rewrite that better, sorry. For this city, the predicted low temperature is 4.2 degrees greater than the observed low temperature. Okay, there you go.